We're ready now to start the last section in chapter 5. When we're thinking about what's called a change of variables, many students mistakenly believe that what we're going to be working with is changing the order in which we integrate something, interchanging dx, dy, dz to dy, dx, dz, or some such. That's not actually what we're going to be doing. When we say change of variables, we do mean a complete change of variables. Now, this is something we've already been doing. You started in Calculus 1 with U substitution. So if you had an integral with respect to x, so that the differential was dx, but you had composition in the integrand, you would set u equal to some function of x. And then you would change the variables and change the differential from dx to du, and the variables from x variables to u variables. You also had to change the limits of integration from x values to u values. We've actually been doing that here in Calculus 3 when we convert from rectangular coordinates into the polar coordinate system. This can be a very challenging section, and the material can be difficult to understand. Fortunately, for all of the work that you have to do, you'll be given what's called the transformation, which is the function that will map one set of variables to another set of variables. And you will be told what the transformation is going to be. You will not have to come up with the transformation on your own. Let me share my screen with you, and we'll get started looking at change of variables. We first encountered change of variables in Calculus 1 when we performed U substitution. U substitution comes into play when you have some kind of composition inside the integrand, one function inside of another function. So for example, your integrand needs to be of the form f of g of x, where g of x is inside f of x, and then it needs to be multiplied by the derivative of the inside function, g prime of x, with the differential dx. Then what we did was we made what we called a U substitution. So we would substitute for the variable u equal to this inside function of x, g of x. When we do that, then we have to replace the limits of integration with the appropriate values. When x is equal to a, what is u going to be equal to? That would give us the value of g of a. And when x equals b, what's the value of u? So it becomes g of b. Let's take a look at an example so we can see more closely what we mean by change of variables. We're going to take the integral from 0 to 1 of the square root of 2x plus 3, the quantity, with the differential dx. Now, we're going to do a u substitution, so we're going to change the variable. It's not going to be x anymore. It's going to be u. So I'm going to set u to be what's underneath the radical, because I have the composition of two functions. The square root of x is the outside, and the inside is 2x plus 3, which is just a line, slope 2, y-intercept of 3. Once I set my substitution to be 2x plus 3, then I compute the derivative so I can replace the original differential dx with something in terms of du. When I do that, I get that du is 2 dx, so I solve for dx to get 1/2 du. So in the original integrand, I substitute 1/2 du in place of dx. I also substitute 2x plus 3 for u becoming what is underneath the radical. Now I need to change the limits of integration. Originally, they were x values to correspond with the differential dx. When x is 0, then I use my definition for u to determine that u becomes 3. And when x is 1, the upper limit of integration, I use the definition of u to get that the u value at the same point is 5. So now I'm going to integrate from u equal 3 to u equal 5 of 1/2 the square root of u du. which is an easier integration to perform. Now, what does this actually mean? What this means is that I have two integrals here, and one of them is defined on the XY plane, and the other one is on what we could call a UV plane. So when we're looking at these two, by saying that they're equivalent, what we're actually saying is the area under the curves over those intervals is the same. So let's take a look at what the area under the curves looks like. So the first one is with respect to X and Y. So we have the square root of X, this function, and we have inside of it 2X plus 3. So the graph here in blue is the graph of our curve, the square root of 2X plus 3. And we want to integrate from 0 to 1, which gives us the shaded region that you see here. Now, if we convert it into something like the UV plane, where V depends on U, then I'm actually now plotting the curve V equal the square root of U, which of course starts at the origin and goes up. It's just your basic square root function. But this says you need to integrate from 3 to 5. And if you integrate from 3 to 5, that shaded region under that curve is exactly the same amount of area as I have under this one. Now, why might we want to change variables? There are a couple of reasons for changing variables, but the bottom line is to make the integration easier. So in the original, when we substituted U for 2X plus 3, it made the integration easier to compute. We could just use the power rule for integrals. What we're going to experience most often here in Calculus 3 is it makes the region over which we're integrating in the UV plane a far simpler region to integrate over. Let's take a look now at what we have been doing in Calculus 3, which is switching into polar coordinate systems. And the same is true of the cylindrical and spherical coordinate systems. We know, for example, that if we have this integrand, this double integral of e to the 1 minus x squared minus y squared power with respect to y and then x, and we integrate from 0 to the square root of 1 minus x squared for y limits of integration, and from 0 to 1 for x limits of integration, we know based on the form of it that we could more easily solve it by switching to the polar coordinate system. So we can define this region in terms of the rectangular coordinate system as x needing to be strictly positive. It goes from 0 to 1. And since y goes from 0 to a positive square root, well, then it also is strictly positive. And we know by solving y equal to the square root of 1 minus x squared that it must be that x squared plus y squared has to be less than equal to 1. In other words, we have a circle of radius 1, and we're looking at integrating over just part of it. So our integrand here is a different kind of function, but the region over which we're integrating is some part of a circle. This leads us to change into the polar coordinate system using the substitution x equals r cosine theta, y equals r sine theta, and we know that x squared plus y squared will give us r squared. Of course, this now means that our differential, which was dy dx, is going to have to change into the polar differential r dr d theta. And we justified this earlier when we used the polar rectangles, but now we're going to learn another justification for why the differential dx dy becomes r dr d theta. We'll see this a little bit later on in the video. So we can rewrite what was in rectangular coordinates into polar coordinates. Now, what is this actually representing? Let's take a look at the graphs and the changes that we're getting from the rectangular system into the r theta system. So in the original, we are integrating over basically a quarter circle, right? In quadrant 1, this is a circle of radius 1. So x goes from 0 to 1, y is limited by the same amount, and it's got to be in this region right here. This is what I'm trying to integrate over. Now I can integrate over it in the rectangular system. It's a little bit difficult. It's easier to do in the r theta system. Why would it be easier? Well, we know from what we've done in the polar coordinate system that r here is varying from 0 to 1. We also know that theta is varying from 0 to pi over 2. But that means that r has limits of integration that are actually just constants. And theta also has limits of integration that are just constants, which means if I plotted that region in the r theta plane, which we have never done to this point, we always graph it as if it's in the xy coordinate system. But by switching the variables from x to y, we're actually switching the region we're integrating over into the r theta plane. And that's just a rectangle, which is super easy to integrate over, as you well know. So it becomes a much simpler integration when we convert the variables from x and y into r and theta. Now, this technique can convert from a not so nice region to integrate over into a nicer region to integrate over, or it can make the actual integrand a simpler, more pleasant form to work with. However, it does change those limits of integration, as we saw in the last example. In the last example, in the polar coordinates, when we changed, notice that the limits of integration on the left in the rectangular system, the inside one, the upper limit of integration was a function that depended on x. But when I converted into the polar system, the r theta plane, both pairs of limits of integration were just constants because I was integrating over a rectangle, which made it far easier to compute. So our job now is to figure out how it affects the integrand and how it is going to change those limits of integration. So one of the things that we're going to have to do is we're going to have to determine what the image of a transformation looks like. So this is called a transformation, where you say x equals r cosine theta, y equals r sine theta. That transforms your variables x and y into variables r and theta. So we have to know what that transformation image is going to look like. So in the example that we just did, the image of the transformation that converted this quarter circle in the rectangular system into a rectangle in the r theta plane, that's the transformation. And this is the image of the transformation. And this is the region I would rather integrate over. So I have to be able to predict what it's going to look like when I get it transformed so that I know how to set up the new integral. That's one of the first things that we'll need to learn how to do and is our first learning objective. As part of that process, though, we often find that the two regions do not have the same area. I mean, it's almost certainly the case that these two regions right here do not have the same area, right? If we look at these regions right here, this goes from 0 to pi over 2. This goes from 0 to 1. So the amount of square area is pi over 2 square units. But if I look at this one right here, this is a quarter circle. So the area of this would be pi r squared divided by 1. So it would be 1/4 pi. That's not the same. So these areas are not the same. The Jacobian is what's going to let us translate from one of these into the other. It says scale factor, which accounts for the fact that these regions don't necessarily have the same area. The length here may not match the length over there for each of the two variables. They're not exactly the same variable. Then we'll use this information to evaluate a double integral and a triple integral using some kind of change of variables. So let's start with the terminology. The first thing we want to define is the transformation itself. we typically will use an uppercase letter T for Tom to associate a transformation that takes one region into a new region. Now, this can also be called a mapping, and you'll hear more about this if you take linear algebra. So basically, it associates some input with some output. In the last example, we wanted all the points in the quarter circle, coordinates x, y, to convert to coordinates u, v inside the rectangle that was in the r theta, in the r theta plane. We wanted them to convert to r theta coordinates. And the transformation is what gets xy to become r theta. So this can be called a mapping, right? So we're mapping a region, a two-dimensional region from one to another. Now, when we do this, we call it a planar transformation, meaning a transformation in the plane, two-dimensional. If it transforms some region G in one plane into a region R in a different plane by changing the variables, maybe going from xy to r theta, or even from r theta back into xy. Now, both G and R have to be subsets of R2, the real plane, and G and R, though, may not be the same. In fact, they're probably not the same. Now we're going to look at an image down here, and the blue region is going to be in the UV plane, and the orange region is going to be in the XY plane that you can see here. So this is region G, which is in UV, and this is region R, which is in XY. Now this is a transformation that takes a point in the blue area and maps it to a point in the orange area. Now, this transformation is given by two functions of the original two variables, u and v. So the first function will convert some equation with u and v and convert u and v into the x coordinate in the new region. And the function h will take u and v with some equation that will generate the value for y in the new region. So this transformation is mapping G onto R. And we would say that G is the domain of the transformation and R is the image of the transformation. But as you know, with functions, if I can go in one direction, I can often go in the reverse direction. And I would call that the inverse transformation, like we call them inverse functions. Now, what we're going to do is we're going to assume that the functions G and H, which convert u and v into x and y, we're going to assume that these functions have continuous first partial derivatives. So the derivative of G with respect to u and v are both continuous, and the derivative of H with respect to u and then H with respect to v, those are also continuous, right? So they all exist and they're continuous. So this is going to be our condition throughout this entire section, that we have continuous first partial derivatives. Now let's talk about what a one-to-one mapping is. You know what a one-to-one function is. It takes some x value from the domain and maps it to one y value out of the image or the range. So when we're looking at the y value, every y value, however, in a one-to-one function came from exactly one x. If the y value gets used, it's in the image of the function. It came from only one x value. Every x has one y, every y has one x. That's what we mean by one-to-one. When we do a one-to-one mapping or a one-to-one transformation, then what we're saying is that every point UV from the original domain maps onto a unique XY in the image. And every XY in the image came from one unique UV out of the domain. And we will call that a one-to-one transformation or a one-to-one mapping. This is very much like a one-to-one function, except that in this case, the transformation actually consists of two functions, one to convert u and v into x and one to convert u and v into y. Now keep in mind that we can go the other direction as well. So I could have one function that converts x and y into u and another function that converts x and y into v, right? So we can go both directions. Let's start with example 1. We're going to define our transformation T of u and v to give us an ordered pair xy, where x is equal to u plus v and y is equal to 3v. And we want to find the image of a rectangle from the UV plane. So technically, we generally want to go the other way around. We want to start in xy and end up in UV. But we're going to go in this backwards direction to make it a little easier to understand how the transformation works. So the rectangle in the UV plane, U is going to vary from 0 to 1, and V is going to vary from 0 to 2. So if we think about what we actually have here, then in our plane, we have a UV plane, and U is varying from 0 to 1, and V is varying from 0 to 2. So it's just a rectangle, all right? So we've got our region here in the plane, and this is one right there, right? So the question is, if I use that transformation, those definitions, which you see right there, so I'm going to write them down again. So we have x equals u plus v, and y equals 3v. So for example, my f, or depending on how you want to write it, my first function f is u plus v, and my second function g is 3v, or you could call them g and h, whatever you want to call them. So the first one is an equation that converts u and v into an x coordinate, and the second one is an equation in u and or v that converts into the y coordinate. So the question is, how do I convert this rectangle using that transformation into another shape? What does it look like in the XY plane? This is in the UV plane, but what would the same region look like in the XY plane? So to do that, the easiest thing to do is just to label the four sides of the rectangle and to think about what happens at each corner here at the four corners of the rectangle and to each side. So the first thing I'm going to do is I'm going to convert side A. So side A is given by the equation up here that V is equal to 2. Now the U value is going to vary from 0 to 1, but V is always equal to 2. So based on my definition of Y, if V is always 2 on that side, then Y will always be 6. Right? So if Y is always 6, then I know that Y value is constant. So it's probably horizontal of some type. And then how does X going to vary? Well, in this case, V is always 2. So I have X equal U plus 2. So if I have X equal U plus 2, what does X vary between? Well, the U value starts at 0. So if I start that at 0, then X starts at 2, and then U terminates at 1. So X starts at 2 and goes to 3. So basically, I have two ordered pairs. I have 2, 6 and 3, 6. Notice that the Y value is 6 in both of them because V is constantly 2. So I need to graph the point 2, 6 and the point 3, 6 and connect them with a horizontal line segment. And we'll call this side A prime to correspond with A. So you can see it right up here. We're connecting 2, 6 with 3, 6, and we call this side A prime. Well, let's go ahead and convert side B. So when we're looking at side B here, you can see the image in the XY plane on the right. If we look at side B here, the U value is a constant. U is always 1, but V varies from 0 to 2. So if u is equal to 1, then in the equation that transforms into x, u plus v, I get 1 plus v. Now, v goes from 0 to 2. So if it's 0, the lowest x can be is 1. And if it's 2, the highest x can be is 3. So x is going to vary from 1 to 3. And when that happens, what's the value of y? Well, y, of course, is equal to 3 times v. But v goes from 0 to 2, so y has to triple each of those. It goes from 0 to 6, right? So when we have this, we have a line segment which is going to connect 1, 0 to 3, 6. So the smallest value here of x and the largest value of x, smallest value of y, largest value of y. Now, I can also use substitution, where I can take the equation here, y equal 3v, and I can solve this equation up here for v and substitute it down there. And you may be saying, well, what happened to the u? Well, remember on side b, u is always 1, so x is equal to 1 plus v. And if as x is equal to 1 plus v, then I can write v equal to x minus 1. And then I can substitute that in place of v here so that I get the equation y equal 3 times x minus 1. So those 2 points are on that slanted line. And you can see that they're connecting the point 0 or 1, 0 to the point 3, 6. So this becomes side b prime. Now we repeat the process looking at side C. On side C, notice that u is varying from 0 to 1, but the v value was always 0. If the v value is 0, then 3 times 0 tells me that y is 0. So it has to be on the x-axis. Now, what points do I connect? What does 0, 0, and 1, 0 convert to? So if I'm looking in the UV plane, then I'm going to be connecting 0 for V. I'm going to get 1, 0. And then, or I'm looking at the wrong one, U plus V. So if U is 0, and I already know, in fact, that V is 0, then I get 0, 0 as well in the XY plane, which is the origin. So this point right here maps to that point over here. It also maps to the origin. That does not always happen, so don't assume that. Now, what about this point right here, which is the point 1, 0? Well, if this is the point 1, 0 in the UV plane, so this is 1, 0, and this is UV, then if x is equal to u plus v, but v is 0 and u is 1, then in the xy plane, the x coordinate has to be 1. What's the y coordinate? Y is 3 times v, so 3 times 0 would give me 0. So it's going to map it to 1, 0, which gives me this side here. So this point maps to that point. And then side D can be found by considering that u is constantly 0, but v varies from 0 to 2. So if v varies from 0 to 2, then y varies from 0 to 6. And x, which is u plus v, is going to basically vary from 0 to 2. So I'm going to be connecting 0, 0 with 2, 6. And you can see that point connecting right here. So this is taking 0, 2, which are the u and v values, and converting it into the xy values, which is going to give us for x, we're going to have 2, and for y, we're going to have 6. So this point right here connects to this point right there. And of course, the one corner I didn't map maps to the other corner. So this is what we call a transformation. So I'm converting from one region to a different region. Now, I wouldn't go in this direction because this one is more difficult, much more difficult to integrate over. The one that's easiest to integrate over is the rectangle. So in my problem, I would start with a parallelogram and convert it into a rectangle in the UV plane and integrate here, right? Now, obviously, these two regions have totally different areas, and the distances that we're traveling aren't necessarily the same. So to compensate for that, we'll develop what's called the Jacobian, which is a scaling factor. In other words, it's a scalar, it's a number. And if I multiply by it, then I can convert something with dx dy into this scalar multiplied by du dv. Because dx dy is not exactly equivalent to du dv, have to have this scalar to make them equal. Let's now move on and talk about the Jacobian. I've mentioned the Jacobian a couple of times. Oh, we didn't finish this problem. So let's go ahead and finish it. The first thing we did was discuss the image, all right? So we wanted to find the image of the rectangle here in the UV plane. What does it look like in the XY plane? What looks like a parallelogram, two pairs of parallel sides. Now we want to show that it's a one-to-one transformation and find the inverse transformation, which is really the direction we want to go. So how can we show that this transformation, x equal u plus v, y equal 3v, how can we show that it's a one-to-one transformation? So let me write down what our transformation definition is again. And y equals 3v. So to show it's one-to-one, we're going to assume that the output of two different values coming from the UV plane, u1, v1, and u2, v2, give me the same ordered pair in the xy plane. So I'm going to start and say I've got 2 points in UV, but they're mapping to the same point in xy. Now, in a one-to-one transformation, that can't happen unless those 2 points in UV are actually the same point. Every point maps to one here, that maps back to one and only one, coming backwards. So what we have to show is that if the transformation of u1, v1, and the transformation of u2, v2, some x1, y1, and x2, y2, if those are equal to each other, then we have to prove that u1 is u2 and v1 equals v2. So in other words, if the outputs are the same, then the inputs have to be the same. So we're going to start with the two assumptions that we have. The first one is that the transformation of u1, v1 equals the transformation of u2, v2. In other words, that x1, y1 equals x2, y2. So x1 equals x2, y1 equals y2. The next thing we're going to do is we're going to apply the transformation here to u and v in order to rewrite it in terms of x1 and y1. So my transformation to get the x coordinate is u plus v. So I have u1 v1 and u2 v2 for each of the two sides. The y is given by 3v, so I have 3v1 on the left and 3v2 on the right. Now, I'm assuming that these are equal. So I'm going to split them into components, and I'm going to say that component 1, the x component, these two have to be equal, and that the y components, 3v1 and 3v2, have to be equal. I mean, that's what it means. This is a consequence of x1, y1, and x2, y2 being equal. Then I can take this equation 3v1 equal 3v2, and divide both sides by 3, which tells me that v1 equals v2. So I'm halfway there. I know that v1 and v2 have to be the same point, but do u1 and u2 have to be the same? So once I've established that v1, v2 are exactly the same value, then I can come back to equation 2 and I can replace my V2 with V1, since V1 and V2 are the same. And then I have U1 plus V1 equals U2 plus V1. But then the V1s cancel because they're the same. And if that's true, then U1 has to equal U2, which proves that this transformation will take one value from the UV plane and connect it or map it, associate it with one value in the XY plane. Now, how can we get the backwards transformation? The backwards transformation means that we need to solve for U and V in terms of X and Y. So I need U equals something with X and Y, V equals something with X and Y. Then if I know X and Y, I can find U and V. So what I'm going to do is I'm going to start with the definition, X equals U plus V and Y equals 3V. And I'm going to solve the first equation for U by subtracting V from both sides. In the second equation, Y equals 3V, I divide both sides by 3. So I get V equals Y over 3. Now that one's good to go because the right-hand side is only in terms of Y. It just can't have a U or a V in it. Now, the first equation is not ready because it's U equal X minus V. And to transform from XY back to UV, I need to have only X and or Y on the right side. So I do a substitution that V is Y over 3, and I can write that U equals X minus Y over 3. Now it's in terms of only X and Y. So my transformation, which I can write as T inverse, applied to X and Y, which will give me U and V, is given by U equal X minus Y divided by 3, and V equals Y divided by 3. So those are my two equations that will take an ordered pair in XY and translate it back to UV. Now, this is the direction we would typically want to go because we don't want to integrate over a parallelogram. They're kind of hard. But integrating over a rectangle is super easy because all your limits of integration are constants, right? Let's now talk about the Jacobian. The issue that we run into in changing variables is that they're not exactly the same region. They don't have the same areas, lengths may not be the same. When we convert using U substitution, we also have a Jacobian. We've just never called it that. When you compute du and you get a constant times dx, and then you solve for dx, you're getting a Jacobian. You're saying that dx is equal to some constant times du. That constant multiplied by du, that's the Jacobian. They're not equal. dx and du are generally, sometimes they are, but usually they're not equal. But if you multiply du by this constant, you get equivalency, right? So the Jacobian takes a little bit to explain. So when we integrate a double integral, we have the differential dA. And we want to move from a more complicated region in the XY plane back to something that's, well, hopefully rectangular in the UV plane, right? So let's start, and we're going to go this direction first. Let's start with a rectangle in the UV plane. And we want to figure out how we're mapping this onto the XY plane. Because if I can go this direction, I can definitely come back. So we're going to do what we normally do in calculus, and we're going to cut up our region into little rectangles. So this region right here actually represents one tiny rectangle. So what we may be looking at out here is actually some larger region, and we've divided it like this. And that orange area S is just one subrectangle, all right? So we have one subrectangle, and we want to know how that one subrectangle translates into a small sub something, some kind of shape over there in the XY plane. So when we're looking at this small rectangle in orange, then on the bottom, we know that this distance, this horizontal distance, is the change in u, which is delta u or du, since the differentials are equal for the independent variables. And the change in the vertical direction is delta v or dv, since again, we're looking at these, or it's actually not equal. Delta v is approximately dv as we make these smaller and smaller. So when I look at the area here on the left, to find the area of S, the orange region, I just take delta V times delta U. But what shape does this translate into? And how can I take this and convert it back? So what is it going to look like? So once I have that, I'm looking at this little small snippet of it right here. And the area in the UV plane is just du times dv, right? So I've got the two differentials multiplied together. But I know that I have a transformation that takes some ordered pair in the UV plane and maps it to some xy in the xy plane using functions g and h. So g of uv gives me the x coordinate, h of u and v gives me the y coordinate. So I can define a position vector of the image of a point uv over in the xy plane. So let's take a look at this. So let's say that I have a point somewhere, uv, and I want to find an expression for this, a position vector, vector valued function, which will give me that vector, but in the xy plane. So let's suppose that it maps to this one right here. How am I going to come up with that position vector? Well, I'm going to apply the function g to u and v to get the x coordinate, multiply it by I hat, and then take h of u and v to get the y coordinate and multiply that by j hat. And that will give me a position vector, which, as you know, in standard form is coming basically out here like that. Now, if we're looking at this, let's suppose that we take this corner spot right here, u naught, v naught, and it maps to x naught, y naught over here. All right, so let me erase the position vector. This point right here in the lower left corner of the orange maps to the lower left vertex of region R in the XY plane. So if that's the case, then everywhere along this horizontal line that I have right here, V is a constant value because it's horizontal. So V is equal to V naught, but U is varying over some range here. So I can represent the image of this horizontal line segment in S over here in the XY plane with R of U comma V naught, where V naught is a constant. Then I can find the tangent vector to it. So the tangent vector at the point X naught, Y naught. So the tangent vector, as you know, is going to point off in that particular direction. The tangent vector is given, of course, by taking the partial derivative. Now, this side is coming because U is varying, but V is not. So I take the partial derivative with respect to U of both G and H and substitute U naught, V naught, since I want the tangent vector at that corresponds to the point U naught, V naught, but translated into the XY plane. So this will give me a tangent vector of the partial of X with respect to U and the partial of Y with respect to U. And that gives me my tangent vector, which you can see down here in the lower right corner. Now, if I want to look at the line where U is equal to a constant, so that would be the left-hand side right here. V is varying over some region, but U is always U naught, so it's a constant, it's not varying at all. I can do the same thing and map this to R of U naught comma V, where V varies, but U naught is a constant. And then I can take, because it's only varying with respect to v, the partial derivative with respect to v, which gives me the partial of g with respect to v at u naught v naught, and the partial of h with respect to v at u naught v naught. Now, the partial of g, of course, is going to give me the x coordinates. So it's the partial of x with respect to v and the partial of y with respect to v that forms the tangent vector at that point. So we've got a little tangent vector coming up like that, right? So I've got these two tangent vectors. And the question is, how can I approximate the area here and scale it so that it's equivalent to the area over here, which is delta U, delta V? So how can I scale these together? So we play sort of a kind of trick where we use the limit definition of the two partial derivatives, the partial of r with respect to u and r with respect to v, which, as you know, is r of u naught plus delta u at v naught minus r of u naught v naught. And then, of course, for all divided by delta u. And then for the partial of r with respect to v, u naught is a constant and v naught goes from v naught plus delta v to v naught. So this is just the basic limit definition of the derivative that we've been using since the beginning of Calculus 1. Now, as long as we're relatively close and we make the rectangle in the UV plane very, very small, then we can approximate the change in the value of r here by moving the denominator delta u to the other side. And in the second partial, by moving the denominator delta v to the other side, so that we can approximate the change in those position vectors with delta, where'd it go? Delta u times the partial of r with respect to u and delta v times the partial of r with respect to v. And this will let us estimate the area of the image r by finding the area of the parallelogram, which is formed by these two sides. So the sides that I have here, coming up here, is I take my tangent vector and I multiply by the scaling factor, delta u and delta v. So this is going to give me the partial of r with respect to u times delta u. And this side right here is going to give me the partial of r with respect to v times delta v, right? So these two vectors will span this region. Now, again, it may not be exactly a parallelogram, but as we make this region smaller and smaller, this becomes more and more like a parallelogram. You know what we're going to do? We're going to add up all the rectangles, take a Riemann sum, and then we're going to take the limit. And as we take the limit, this region becomes more and more shaped like a parallelogram, so that this approximation of the area becomes exact, right? So how are we going to get this cross product? Well, when we get the cross product, we're basically, to do a cross product, you have to have a three-dimensional vector. That's the definition of the cross product. So we just add 0 for the third component. We have ijk here. And of course, the k's are both 0. And then we can compute the determinant, pseudo-determinant of the 3x3 matrix to find the area of that parallelogram, because the area of a parallelogram is given by the magnitude of the cross product. So to find that, we can compute the cross product and then find its magnitude, right? So let's take another look at another way of thinking about this. Think of it this way. We're going to take a square or a rectangle on the left and convert it into a parallelogram on the right. So when we map this horizontal blue line on the left into this blue vector on the right, it becomes the partial derivatives with respect to u multiplied by the scaling factor du, right? So our partial derivative, this partial of x with respect to u, comma, partial of y with respect to u, becomes a scaling factor multiplied by du. Over here, it is just du. But over here, it becomes this. So that we have this scaling factor on it to make them equivalent. And then we do the same thing for the vertical red line segment in the UV plane, which converts into a scaled value over here on this side. All right. So when we map these two, then we can come up with this parallelogram. And to find the area of the parallelogram, we compute the cross product. And this is basically going to give us the 2 by 2 determinant of this matrix multiplied by k hat. And notice that the du and dv came out as sort of like scalar multiples. So this is going to give me that transformation of the area from one to the other. Now, when I do this, we call this matrix that you see right here, this partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. We call this matrix the Jacobian matrix, right? Now, unfortunately, we also refer to the value of that determinant, the magnitude of it. We also call that the Jacobian. So I'm going to call this the Jacobian matrix, and the magnitude of the determinant I'm going to call the Jacobian, all right, without a qualifier on it. So the Jacobian, this determinant, the magnitude of the determinant of that matrix is what converts, gives us that scaling factor. Very much like what we had when we were looking up here at our original u substitution, and we were converting from one to the other. Do you see here that this dx equals 1/2 du, and the 1/2 is the scaling factor, the Jacobian, that converts from variables in x and y to variables in u and v. So we've been working with a Jacobian, we just haven't called it that. So let's go ahead and formally define the Jacobian here. So we're going to take a transformation acting on some ordered pair in UV, taking it to some value of x and y. So this is giving me some x comma y, where x is g of u and v and y is h of u and v, and they have continuous first partial derivatives. We typically use the notation uppercase letter J of u and v, or weirdly, we use the partial notation, although it's not really a determinant. I mean, it's not a derivative, it's not a partial, but we use that symbol, which looks like the partial of xy with respect to the partial of uv. And that is defined to be the 2 by 2 determinant that we had above. And it turns out that you can either have the partials of x both in the first row or both in the first column. You get the same value either way. So you can use whichever form you prefer. I typically like to have all my x's in the first row and all my y's in the second row. It just makes it a little bit easier. And of course, remember that to do the 2 by 2 determinant, it's the major diagonal minus the product of the minor diagonal, which gives you that formula that you see there. But typically, we just think of it as the determinant of the 2 by 2 matrix. Now, these straight bars right here, of course, are representing the determinant operation. All right, so finding the determinant, which is the product of the major diagonals minus the product of the minor diagonals. However, when we convert from one to the other, we're talking about converting an area. An area can't be negative. So what we really want from the Jacobian is a positive or at least non-negative value. In fact, we really do want a positive, because if the Jacobian is 0, the integrand will 0 out and we get nothing. So we really want the Jacobian to be positive, in which case we want its absolute value. These bars right here do not represent the determinant operation. These bars represent the absolute value. So you have to kind of know which one is which. So when it's applied to something that looks like a matrix, it's probably the determinant operation. But when it's being applied to a number, it's the absolute value operation. And the Jacobian does end up being a number. So when we look at it, this Jacobian is what converts the area differential dA, which is dx dy, into a differential with du and dv. So it's the Jacobian's absolute value times du dv, which is equal to dA or dx dy. So this is similar to what we had in u substitution when we said du was g prime of x dx. Right? So we had this scaling factor, which let us convert, as we saw previously, with dx equal to 1/2 du. So the 1/2 was our scaling factor, our Jacobian. Now we can also extend this definition into functions of 3 variables as well. And if we do that, again, you can do it in either format. You can have all the x's in column 1 or all the x's in row 1. All the y's in column 2 or all the y's in row 2. I tend to prefer the last method. I think it's a little bit more common in most textbooks. So that's the one I'm going to use, where I have all the partials of x in row 1, all the partials of y in row 2, and if it's 3-dimensional, all the partials of z in row 3. And then with respect to u, v, and w, depending on how many independent variables we have. Now let's go ahead and take a look at finding the Jacobian of a particular transformation. And this first time I'll write out the 2 matrices so that you can see that in fact they are always going to give you the same value. So for example, this first one has the partials of x written in column 1 rather than row 1. So the partial of x with respect to u, if I look at x's definition, it's u plus v. So the partial of x with respect to u would just be a 1, right? And then the partial of x with respect to v would be 1 as well. So that would go in row 2, column 1. And then the first one, the partial of y with respect to u, y doesn't have a u in it, y equals 2v, so the partial is going to be 0. And then the partial of y with respect to v is just going to be 2. And then to find the 2 by 2 matrix, I take 1 times 2 minus 0 times 1, which gives me 2. Now, would I have gotten the same thing if I'd written it in the other format, where row 1 consists of the partials of x? Well, let's try it. Partial of x with respect to u, we said that that would give me a 1, and the partial of x with respect to v would also be a 1, but this time it goes in row 1, column 2. Partial of y with respect to u is 0. Partial of y with respect to v is 2. And then this becomes 1 times 2 minus 1 times 0, which is still 2. So you can see that we get the same value no matter which way you do it. But my advice is pick one and stick with it so that you can remember it long term. All right. So the next thing we want to do is we want to find the Jacobian on the polar transformation. This is the transformation that takes r theta back to x and y. So we want to confirm that the differential dA, which is dx dy, becomes the polar differential r dr d theta. We want to see, where did that r come from? Why isn't it just dr d theta? So what we're going to do is we're going to apply one of these to the transformation, find the 2 by 2 determinant, and that will tell us what the Jacobian is, which is the multiple that we'll have to multiply by dr d theta to convert dx dy into the r theta plane, all right, or backwards. So go ahead and pause the video to work that out, then turn the video back on and we'll look at it together. So in example 3, I used the second form where I have the partials of x with respect to r and theta in row 1, the partials of y with respect to r and theta in row 2. So the partial of x with respect to r, since x is r cosine theta, just becomes cosine theta. And the partial of x with respect to theta is negative r sine theta. Then r, or y, is r sine theta, so the partial of y with respect to r is just sine theta, and the partial of y with respect to theta is r cosine theta. And this gives me a 2 by 2 matrix, which is the Jacobian matrix. And I want to find the determinant by finding the product of the major diagonal minus the product of the minor diagonal, which gives me r cosine squared theta plus r sine squared theta. And I factor out the r, cosine squared plus sine squared gives me 1, and I end up with r. So r is the Jacobian, which translates moving from r theta into xy, so that the differential dA, which I can replace with dx dy based on a rectangle, becomes the Jacobian r times the differentials dr d theta to take it into the r theta plane. So this is the reason why we have r dr d theta when we convert into the polar coordinate system.